Tunda, 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 pa, 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 pa. Spray him, nigga. Okay, it's gonna be a wonderful stream. I'm doing a sorted array. So, no. I think I might need
Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So we will be continuing with our binary search series, which is the part of the Strivers A to Z DSA course. Just in case you haven't checked it out yet, there's a link in the description. I'll highly recommend you to check it out. So till now I've covered up till this particular problem. In this video I'll be covering up the problem search in a rotated sorted array. So what does the problem state? It states that you have to search in a rotated sorted array. Now what is the definition of rotated sorted array? Let's understand. Imagine I give you an array like 1, 2, 3, 4, 5. Now this is a sorted array. Now I ask you, can you
Hey everyone, welcome back and let's write some more neat code today. So today let's solve the problem search in rotated sorted array 2. I solved the first one of this I think like 3 years ago, and this problem is almost exactly the same as the first version, so I will kind of summarize the solution for that one. But I will say that this problem is pretty damn hard for a medium problem. The main difference is we're given a sorted array of numbers. In the original problem, these numbers were in increasing order. So if you draw them like a graph, it would look like this, where each value is always going to be increasing. This time we're given a non-decreasing order array, so actually it might look something like this, where we have like a flat line somewhere, and we could actually have potentially multiple flat lines like this. And this makes the problem a lot more complicated, and I'll show you an example of why that is. To quickly summarize, again, this array is going to be rotated. So for example, if we had an array 1, 2, 3, 4, to rotate it is basically to cut it in half somewhere and then take this portion, the right portion, and reverse it. Well, not reverse it, but just like switch them around. So the rotated version of this would look something like 3, 4, and then 1, 2. This time it's rotated from exactly in the middle. Now we're also given a target value, and we want to determine if the target is within the array or not. Now that's a simple problem to solve. Why not just linearly scan through the array? Yep, that's pretty easy. You can do it in big O of n time. But of course, the fact that this array is sorted, we can use that to our advantage. In the original problem, we were able to solve it in log n time. And the reason we were able to do that is we set up a binary search, a traditional one, where we have a left pointer at the edge and a right pointer at the other edge. We calculate a midpoint, and I think in this case, our mid would be here because we take the left and right, add them up, and divide by 2. Now I mentioned in the problem we solved the other day that if you take left and right, add them together, that can potentially overflow before you're even able to divide it by 2. So another way to calculate this is actually to take left plus right minus left and divide that part by 2. Now why does this work? Well, think about it. We have a picture this time, so it's a little bit easier to understand. What we're doing here, taking the difference between them. Basically, we're taking the length of this subarray and we're taking that and then we're dividing it by 2. So kind of like this, right? We're taking this part and then adding it to the left pointer. So in this case, I think right is equal to 3, left is equal to 0. You take 3 minus 0, you're going to get 3. And you take 3 and you divide it by 2. We end up rounding down, and I think that will be a 1. So we basically get the exact same answer. Left plus 1 in this example, which we'll put mid over here. That's the idea, but that's just a little bit of math. It's not a big deal. But to get back to the problem at hand, how are we going to use the fact that this array is sorted, or at least 2 parts of this array are sorted? How are we going to use that to our advantage to run a binary search? Well, it would be nice if we can identify which portion of the array we're in. Remember in this example, well, I guess I didn't even mention it, but let's say our target in this case is equal to 1. I'll be changing this just to illustrate how the binary search is going to work. Of course, the first thing to check would be, is the value at the middle pointer equal to the target? No, it's not. Now, the hard thing here is, how do we know? Should we search on the left side or should we search on the right side? If it was a basic sorted array, we just compare the target with the middle value. It's not that simple in this case, but the first thing to know, to recognize would be, well, are we in the left portion of the array or are we in the right portion of the array? What I'm going to do right now is basically just run through every possible scenario. Basically, what we're doing here is just a bit of discrete math, really, because it's not like there are infinite possibilities. There are a discrete set of possibilities, and we're going to run through each of them to make sure our algorithm works. Now, in this case, we are clearly in the left sorted portion, but how would we know that? By looking at every element, it's pretty obvious, but how can we know that algorithmically, and how can we do it efficiently? Well, think about it. The left value is always going to be less than the middle value if we're in the left portion. Now, if our middle pointer was over here, that would not be the case. 3 is not less than 1. So that's the way we know it. It's very easy. All we do is check is nums at left index less than nums at middle index. Then we are in the left side of the array. If this is not true, then we're in the right side of the array, or in other words, if the left value is greater than the value at the middle. And again, that's pretty obvious if our middle value is over here, because we know every value over here is going to be less than this value because the array was sorted and then we rotated it. By definition, all of these guys are going to be smaller than this guy. And this is the part where you might start to realize why the original solution won't work on this problem. Because like I said, by definition, this is going to be the case if the array was sorted. But this one was in non-decreasing order. It wasn't in sorted like an increasing order. So actually, we won't know that, but I'm not even going to cover that just yet. Let's just try to really understand how to solve the first version of this problem. So now we have a way to know whether we're in this side of the array or we're in this side of the array. How do we use that to our advantage? Well, once again, it's pretty simple once you actually know it. Let's say this part of the array is sorted from left to mid. Well, the obvious thing to do is check, is the target value within that sorted range? It's pretty easy. Again, just check if the number at the left pointer is less than or equal to the target, and also check, is the target less than the value at the middle pointer? So this inequality we're checking is the target in between that range. If it is, it's pretty obvious what we should do, right? We should take our middle, the target value within that sorted range. It's pretty easy. Again, just check if the number at the left pointer is less than or equal to the target, and also check, is the target less than the value at the middle pointer? So this inequality we're checking, is the target in between that range? If it is, it's pretty obvious what we should do, right? We should take our middle pointer, we should start searching to the left of the middle pointer, and usually with binary search, we do that by taking our right pointer and setting it to mid -1, so it'd be set over here. Now, clearly in this example, that is not the case. This inequality is not true. What does that tell us? That tells us that if the target does exist in this array, well, it's definitely not going to be in this portion. So what do you think we should do? Search on the right side. How do we do that? Take our left pointer, set it to mid +1. It's going to go over there. So it's going to cross these guys out because we don't need to consider them anymore, and our left pointer is now going to be over here. And at this point, we'll be able to find the solution. But I want to run through the other cases as well. Suppose our middle pointer was actually over here, and let's say our target this time is actually equal to 3, just to make things interesting. If it was 1, then of course we just found our solution. But let's say it's 3. What do? Well, we have a way to recognize we're in the right sorted portion of the array. So what do? We check, is the target within this range? Is it would cross, set it to be over here to mid -1, so it would be over here. And then we would be able to find the solution here because we're going to find that we're in the left sorted portion, and we're going to find that 3 does lie within this range, and then we would cross this guy out, and eventually we would find that 3 is over here. So that's how we solve the original problem. But let me show you an interesting example. It's pretty basic. Let's say I have 1, 2, 2, a bunch of repeated values, and a 3. And let's say I rotate it so that it looks something like this, where the 1 is over here. So we kind of rotated it from this part, like this is the pivot. So just redrawing it, this is our rotated array. Now, let's say our left pointer is here, right pointer is here, our middle is over here. The hard part here is that we don't know whether we are in the left sorted portion or the right sorted portion, because remember, originally we were doing that by checking if our middle value is greater than the leftmost value, then we're in the left sorted portion. We can't do that because now they can potentially be equal. And it's even more obvious if I take the rotated sorted array and actually rotate it about the middle so that it looks like this, where the 2, 2, 3 is here, and then the 1, 2, 2 is there, because potentially you can imagine our middle pointer might be here for some reason. Like assuming we had a much larger array, maybe our middle pointer ends up here and our left guy is over here. We don't know, does this 2 belong to the left sorted portion? Like, is this just a string of 2s, or is this middle pointer over here? It's in the left sorted portion, and then, there's gonna be a pivot, and then there's gonna be values here. Like, look at this. We have 2s on both sides. I'm sure you realize why we can't do the original solution now. We don't know which side of the array we're in. Therefore, we can't potentially just eliminate half of the array. So knowing that, how are we going to be able to solve this problem? Are we forced to do a linear scan? Well, it kind of depends on the input. Like in this case, where the middle is equal to the left value, it's true. We don't know which portion of the array we're in. So the best we can really do is say, well, we looked at the middle value. This is not the target. So theoretically, we could eliminate that, but that makes binary search very hard. So we're not actually going to do that. But we recognize that since this value is equal to the left value, that's the reason we can't do binary search, but that also is convenient for us because they're equal. This value is equal. So therefore, we know that this can't possibly be the target because this was not the target. So then we would just eliminate this and then take our left pointer and shift it over here and then continue our algorithm here. And the reason we're doing it this way is because in some cases, we can run binary search. In some cases, we will be able to eliminate half of the array. And as I continue running it on this example, you'll see. I'll just redraw this really quickly just to make it a bit more readable. But now we're going to take this left pointer and shift it by 1 so that's over here, which would basically mean, like in this example, our left pointer is going to be here and our right pointer is going to be here. We recalculate the middle, it's going to be here again. And once again, this is equal to the leftmost value. So we can't determine whether we're in the left portion or the right portion. Knowing that, what are we going to do? Once again, we're just going to eliminate the leftmost value. So taking our left pointer now and shifting it here, this is where things are going to get a bit more interesting. Well, actually not yet. Once again, our middle, I think is going to be over here, same as the left. So once again, we shift it. So left is now finally going to be here. Now things get interesting. Now our middle pointer is going to be here. We're going to find that we are in the left sorted portion. And I didn't even mention what our target was, but let's say our target is actually equal to 1. What we would do is same thing as we did in the original algorithm. We're going to check if 1 is within this range from 2 to 3. It's not in this case. So therefore the target is definitely not going to be in this sorted portion. This is the Our left pointer is now going to be mid. We're not calling it left. We can update. We're going to search cases, right? So if we find our result, we're going to return it up here. But if we don't find it, we'll exit the loop and we'll return -1. One.
Hey guys, Greg here. Let's solve first bad version, LeetCode number 278. So we're a product manager and we're currently leading a team to develop a new product. And unfortunately, the latest version of our product fails the quality check. And since each version is developed based on the previous version, well, all the versions after a bad version are also bad. So once it got bad, it was bad all the way there. So suppose you actually have n versions, they're calling it 1, 2, up to n, and you want to find out the first bad one because we want to find where the problem is. So this is the one that causes all the following ones to be bad. Well, we're given an API, which is just a function. It's a function that returns a bool, which is either true or false. So we have this function called isBadVersion that takes a version number, and that'll return whether the version is bad. Now we need to implement a function to find the first bad version. And it's giving a little hint here. You should try to minimize the number of calls to the API, and there is a good way to optimize that. Okay, so just to make sure we understand here. So if you have n equals 5 versions and the first bad version was version number 4, by the way, that's not like a parameter to the problem because that's the thing you'd actually want to return. You'd want to return 4 because, I mean, they're not actually showing it all here, but is bad version of 1 and 2 and 3 would all be false because we're saying like, are those bad versions? No, they're actually good versions. And so is bad version on that would be false. Is bad version on 4 would return true because that is a bad version. And so it is on 5. The first bad version would be version number 4. So before we visualize the more optimal optimal solution. I just want to code up the version. So that's really all that you have to do there. And that's not going to pass the test cases because it's too slow. So these are all of our version numbers that if binary set the first 5 binary for everything version equal L this actually want to leave. So we're only going to a bad version. We wrote down that we want to keep that it's a bad version, and so we don't want to lose that. We just set R equal to M. However, if it's not, so if it is a good version, well, then we don't want a good version. So we'll move past those. L is equal to M plus 1 to discard as many of those as we can. This will keep running, and eventually we will get to the fact when we do hit the first bad version and they're going to be equal to each other, so we can just return either L or R because they're going to be
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve first and last position of an element in a sorted array. So we're given an array of numbers and they're in sorted order, in ascending order, and we just want to find a certain value, so a target value that we're looking for, and we want to find the starting and ending index of that value. So in other words, there could be multiple copies of this target value in our input array. And if we cannot find the target, then we can just return -1 as the start and ending indices. But so let's look at the first example. So we have a target 8, and you see that there's 2 8s in our example. And the index of them is, so we're solving, which say that this, we don't update the middle, and we're going to update the left pointer because we know 8 is what we're looking for, but 7 is too small. So we're going to start looking at the values to the right of the array. So we move our left pointer over here. We don't have to consider these values anymore. So now when we recompute the middle, we're going to put it over here, right in between the left and the right. And now we look at the value over here, but our algorithm would stop here. And if this value was 8, then we would want this and this, the indexes of these two positions, right? So how are we going to handle that? Well, we can modify our binary search algorithm. So let's actually assume that this value is 8. And we have where what we write there in the pit and we go to index and then return that. So let's get left by calling our binary pointer code. Let me just prove.
Hi, how is it going? Welcome to Code with right. That's gonna be equal to looping because left. Alrighty, let's go. This is smaller than nums of mid. So if we didn't find the number that we were looking for, and
Hello and welcome. Today we're doing a question from LeetCode called find first and last position of element in sorted array. It's a medium. We're going to jump right into it. Equal left plus right, integer divided by 2. So we want to go 7. So first is going to be index 2. We don't move our mid, left plus right. So 4 plus 5 is 9. Integer dividing that by 2 is going to be our indices. We want to bias up and we want to round up. If we add now 4, we go back in this while loop target, search, passing in our left and right bound. So it's going to be
Hey everyone, welcome back of pass in index. We're going to pass in true for left bias, and then let's get the right one. And let's pass in false since this is going to be right biased, and then we can return our left and right pointers. And by default, if we can't find the result in this binary function, it's going to return -1, which is exactly what they wanted us to do. So this is actually the entire code. Let me just prove to you that it works and prove to myself that I don't have any bugs in it. And yes, it does. So you
This section is about graphs. So we'll learn various things about graphs. But in this video, we will have introduction to the terminology used in graphs. For introducing terminology, I have taken various example graphs. So through these graphs, let us know the terminology. This section is about trees. So we learn about general trees and binary trees and various types of binary trees. So in this video, we'll learn about the terminology of trees and introduction to binary trees. So let us start with terminology. See, here I have taken a general tree and nodes are containing alphabet so that it's easy for you to understand. Let us define a tree. Tree is a collection of nodes or vertices and edges. Nodes and edges. These links are called as edges. If there are n nodes, then there will be n-1 edges. Because for each node, you can see that there's an edge coming over that node, there's an edge coming over that node. Every node, there's an edge coming from its parent, except root. Root is not having an edge coming from any parent because that is the parent of all the nodes. So if there are n vertices, then there will be n-1 edges. This is a root node for the tree. And if I look at only this portion, all the nodes below B, then this is a subtree. D and all the descendants of D, all the nodes below D is a subtree. So if I define a tree, tree is a collection of nodes. Among those nodes, one node is taken as root node. Rest of the nodes are divided into disjoint subsets. They are in subset. This is one subset, this is another subset. There is only one node in the subset. And each subset is a tree again or subtree again. So I repeat the definition. Tree is a collection of nodes where one of the nodes is taken as root node and the rest of the nodes are divided into disjoint subsets and each subset is a tree or subtree. Now let us look at the terms. First, root. The very first node on the top is a root. Parent and child. A node is a parent to its very next descendants or those children which are connected with just one edge, or those descendants which are connected with one edge. So for B, E and F are its children. For D, G, H, I are children of D. So D is a parent of G, H, I. N and O are children of L. L is a parent of N and O. So we have finished these. Now siblings. Siblings are children of same parent. G, H, I are children of D. So they are sibling to each other. G, H, I are siblings. J and K are siblings because their parent is same. N and O are siblings. Next, descendants. For any node, the set of nodes which are its children and their children and their children, so on. Or in other words, descendants are all those set of nodes which can be reached from a particular node or under that node. For example, for B, E, F, J, K, M, all these are descendants of B. For L, N and O are descendants. For D, G, H, I, L, and O, all the nodes that are reachable from D, descendants of D. Next is ancestors. So for any node, all the nodes along the path from that node to root node. So for M, J, F, B, A are ancestors. For N, L, H, D, A are ancestors. The next is degree of a node. Degree of a node is number of children it is having, direct children, not all descendants, direct children. Degree of L is a 2, it is having 2 children. Degree of D is a 3, degree of A is 3, degree of F is 2, degree of J is 1, and degree of N is 0, K is 0, M is 0. Number of children any node is having is the degree of a node. Then what is the degree of a tree? From the tree we cannot tell what is the degree. Degree is pre-decided. But if you observe, what is the maximum degree of any node? 3. See, this is having 3 degree, this is having 3 degree. So the degree of a tree can be minimum 3. Minimum, at least it is 3, or it is more than 3 also. So I can explain you afterwards. Then coming to internal nodes and external nodes. Internal nodes, external nodes are also called as non-leaf nodes and leaf nodes, or terminal nodes or non-terminal nodes. What are those? Nodes with degree 0 are called as leaf nodes. Degree 0, degree 0, degree 0. So E, M, K, G, C, N, O, I, all these are leaf nodes or external nodes or terminal nodes. And those nodes whose degree is greater than 0 are internal nodes, non-leaf nodes, non-terminal nodes. Next, levels. See, level of a tree starts from 1 onwards, that is root is at level 1, then its children are at level 2, and their children at level 3 and 4 and so on. So level starts from 1 onwards. So actually, for level, we count nodes. Here one node, horizontally if you see, there is one node. Then at this level if you come, total 2 nodes are there. Either you count this 2 or this 2. We don't count all nodes, just the path. In the path we will count 2 nodes. Until here, the path from root, that will take 3 nodes, 1, 2, 3. Either you come here or you come here, anywhere. At this level, there are 3 nodes, 1, 2, 3 nodes. Then at this level, there are 4 nodes, 1, 2, 3, 4 nodes. So we take the path by taking number of nodes. So that's how it is levels. The next is height of a tree. Height of a tree, I will mark it here on this side. Root is at height 0 and its children at height 1, then height 2, then height 3 and 4. See, here we count edges. Till here there are no edges. Now if you come down to this next level, or let us say level only, or path, either you go here or here or here, then how many edges are there? One edge is there. So this is taking 1 edge to reach here. 1 edge to reach here at this horizontally at this level. 2 edges are there. So 1, 2 edges. Then till here 3 edges, then 4 edges. So level starts from 1 onwards and the height starts from 0 onwards. Height and level both are useful for analysis. Now coming to the last term, that is forest. A collection of trees is called as a forest. For example, here I will make a change. I have removed A. Root I have removed. How many trees do you see?
This is one, then this is just in single node tree, and this is another. Total 3 trees are there. So this is a forest. Collection of trees is a forest. And if at all you want to make it as a tree by combining all the forests, then you can introduce a node like this. So here, a forest is converted into a tree. So forest is collection of trees. So that's all with the terminology. Now I will introduce you to a binary tree. Now let us learn about binary. Tree. A tree of degree 2. Degree 2 means every node can have maximum 2 children, not more than 2 children. It can have less than 2 children, but not more than 2 children. So degree of a tree must be 2. If the degree is 2, then it is called as binary tree. By 2. So 2 children. So every node can have 2 children. A is having B and C. B is having D and E. Likewise, C is having F and G. As there are only 2 children, we will give the names to the children. This is left child and this is right child. So for B, this is left child and this is right child. So we give names as left child and right child. One more definition of a binary tree, that every node can have either 0 children or 1 child or at most 2 children. So children can be either 0, 1 or 2, not more than 2. Let us look at some examples of binary tree. I will draw some binary trees. I will not label them. This is labeling A, B, C, D. Just I will draw dummy nodes and look at the shape and find out whether it is a binary tree or not. Here I have some binary trees. First one, is it a binary tree? This is not having any children. Yes, every node can have 0, 1 or 2 children. How many children is having? 2 children. Okay, perfect. How many children? 0. Perfect. 2 children. Perfect. 0, 0. Everything is perfect. What about this? This node, 1 child. Yes, perfect. 0, 1 or 2. Remember this. This node, 1 child. Okay, perfect. This node, skew. Any node is a binary tree. This one is not a binary tree. Then what about fifth one? See this tree, just rotate it with some angle. This is same as this one. Yes, we draw the tree like this also. Instead of drawing left, right child, we draw down and right child. So this shape is also possible. So we draw a tree like this also. So binary trees are more commonly used. There are various forms of binary trees. We'll be learning them slowly. So in this video, we have finished the topic. I have discussed the terminology and introduction to binary trees. The topic is number of binary trees for a given set of nodes. It means if suppose some number of nodes are given, like 3 nodes are given, then using 3 nodes, how many different binary trees can be generated? We are going to learn that. We will learn about 2 types of nodes, that is unlabeled nodes and labeled nodes. Let us start with unlabeled node. This is an example of unlabeled nodes. These are empty nodes. Labeling is not there. Alphabets A, B, C or numbers 1, 2, 3, nothing is written in that. So these are unlabeled nodes. So if 3 nodes are given, how many different binary trees can be generated? I will draw them and show here. This is one shape, first one. Second shape, that is root, left and its right. Third shape with 3 nodes. Now next will be a mirror image of this one. This is the fourth one. Next will be mirror image of this. There are 5 different trees. So if there are 3 nodes given, number of trees, if it is a function, then the value of this function is 5. So if there are 3 nodes, we can generate 5 different shaped binary trees. 5, 1, 2, 3, 4, 5. Next, if there are 4 nodes, then how many different shaped binary trees can be generated? So I'll take 4 nodes, number of nodes are 4. These are 4 unlabeled nodes. I will draw different shaped binary trees here. So here I have generated few. Look at them. First one, second, third, fourth, fifth, sixth, 7. I have drawn 7. Then I can take the mirror images and I can draw 7 more. This is one shape. So this is left skewed. Then also I can have right skewed. Right? So for each I can have a mirror image. So 7 more I can draw. So I will complete that. Now I have all 14 trees. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 different shapes of binary trees. So it means if number of nodes are 4, then we can have 14 different shaped binary trees. So for 3 nodes, we got number of trees as 5, and for 4 nodes, we got the number of trees as 14. Then for 5 nodes, how many it will be? For 6 nodes, how many it will be? Shall I draw every time and check them? No, just for observation I have drawn them. To explain you what does it mean by number of trees, I have drawn them, right? Now there must be some formula for this one. Yes, there is some formula. That formula is number of trees for given number of nodes are 2n Cn by n plus 1. This is a famous formula. The name of this formula is Catalan number. This is a known formula. 2n Cn by n plus 1. So if n nodes are given, then these many number of binary trees can be generated. So for 5, how many? Let me calculate. T5 will be 2 into 5 C5 by 5 plus 1. This is 10C5 by 6, 10C5 by 6. And this is 10 into 9 into 8 into 7 into 6 divided by 5 into 4 into 3 into 2 into 1. The whole thing divided by 6. Now let us divide this and get the answer. 6 gets cancelled. 5 2's, 10 is gone. 4 2's, 8. And 3 3's, 9. So this is 3 into 2 into 7 is remaining here. So this is 42. So T5 is 42. So for any given number of nodes, you can find out how many different shaped binary trees can be generated. If at all you want to try out and see how those trees looks like, then you have to draw all of them. That may not be practical, so I have just shown for 3 nodes and 4 nodes. Now one more observation I have to do here. See, when 3 nodes are given, what could be the maximum height? Height starts from 0 onwards. So 0, 1, 2. So 0, 1, 2. So the maximum height possible is 2. This tree is of height 2 and 2, and this is not a 2, this is 1, 2, 2. So how many trees are there with maximum height? 1, 2, 3, 4. So the number of trees with maximum height are 4, so that is 2 square. This is for how many nodes? N equal to 3 nodes. Then what about n equal to 4 nodes? Number of trees with maximum height. Let us count them. 0, 1, 2, 3. Yes, this is maximum height because there are 4 nodes, so the height should be maximum 3. So 1, 2, 3, 4. This is not maximum. No, 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 no. Yes. 5, 6, 7, 8. So 8 trees are there with maximum height. So this is 2 cube. So for n equal to 5, how much it will be? You can guess now. 16. Yes, this is 2 power 4. So for any n, how many trees will be there? 2 power n minus 1. So we have learned how many different shapes binary trees can be generated for given number of nodes. So we don't have to generate the tree, we can use the formula. And one more observation we did, then how many binary trees are possible with maximum height? So that is 2 power n minus 1. Now next, let us generate one more formula for Catalan number. So I will write down few values of a Catalan number. Then from that, let us see how we can come up with one more formula for Catalan number. So first of all, I will take the table of values for Catalan number. See, if n is given, then Catalan number Tn, that we know the answer formula 2n Cn by n plus 1. So 8, see here value of n, and this is the Catalan number. So I will take the values of n and write down the Catalan number values also. So if it is 0, then if you put 0 in this formula, you get 1. Then if it is 1, then it is still 1. For 2, it is 2. For 3, we know the answer directly, just now we saw. Then for 4, it is 14. For 5, it is 42. So for 6, I will find out using a different method. I will not use this formula. So just watch this one. I want the answer for 6. So for that, I will multiply these values. 1 into 42 plus 1 into 14 plus 2 into 5 plus 5 into 2. See, it was 2 into 5. Now 5 into 2 plus 14 into 1 plus 42 into 1. This gives the answer for 6. So the result of this one is 132. Let us use the formula for value 6 and check whether our answer is correct or not. Let us verify. T6 is 2 into 6, 2n Cn, right? 2 into 6, C6 by 6 plus 1. So this is 12 C6 by 7. This is the numerator, then the denominator will be 7. Let us cancel these. 7 gets cancelled. 6 2's 12 gets cancelled. 5 2's 10. 4 2's 8. 3 3's 9. Remaining is 11 into 2 into 3 into 2. So this is 11 into 2, 3, 6, 6 2's 12. So 11 into 12, 132. So yes, we got the correct answer. By substituting in this formula also, we got the correct answer. So how I got this one? I multiplied this one with this one, and this one with this one, then this 2, then this 2, then this 2, then this 2. So let us prepare a formula for that one. So this is T6. So this is T0 into 42 is T5. T5 plus T1 into T4, then T. So the T values we are multiplying, right? So T2 into T3, then T3 into T2, then T4 into T1, then T5 into T0. So these are the terms, and each term is a product of two values. So this can be written in general form. Tn is a summation of two values, T of something into T of something. So what is this? This starting from 0, 1, 2, 3, 4 up to 5. And this is 5, 4, 3, 2, 1. So one side it is increasing, the other part is decreasing. So this is increasing, this is decreasing. So if I take I value starting from 1 to n, then I should say I minus 1. Because I is 1 means first time it should be 0. And this is n minus I. So yes, we got the formula. So Catalan number Tn is 2n Cn by n plus 1. 2n Cn by n plus 1. This is one formula. And the other one is summation of I takes values from 1 to n, I minus 1 into T of n minus I. So the Catalan number can also be written like this. This is a combination formula and this is a recursive formula. So that's all about the formula, Catalan formula. We have got two formula. Now we have to learn about labeled nodes. So I will remove this, then I'll explain you about labeled nodes. Now let us see labeled nodes. Labeled node means these three nodes are there. Now you can see they are labeled, right? In the previously, there were no labels here. They were blank. Now something is written in that. So labeling is done. So A, B, C are labels. Then if labeled nodes are there, then how many different binary trees can be generated? That's what you have to find out. So without label, already we know the answer. Without labels, there are 5. And the formula is 2n Cn by n plus 1. We already know the formula. This is the formula. And for 3 nodes, answer is 5. But no, these are labeled. So labeled means if I pick up just one tree, this tree if I pick up, then this is unlabeled. So if I try to label it, how many ways I can label it? 3 labels can be filled in how many ways? 3 factorial ways. Let us see. Just I will label this A, B, C. And one more labeling A, C, B. Same tree, shape is same, but the labels are changed. Permutation of label has changed. So I have different ways of filling ABC, ACB, BAC, BCA, CAB, CBA. So 1, 2, 3, 4, 5, 6. So yes, these are 6 means this is 3 factorial. So one shape can be filled in 3 factorial ways. Second shape again 3 factorial, 3 factorial, 3 factorial. So every shape in 3 factorial ways. So for 3 nodes, 3 factorial. For n nodes, n factorial. This is the formula. So for labeled nodes, formula is 2n Cn by n plus 1 into n factorial, because the filling of labels. So if you look at this formula and separate it into 2 parts, this part is for shapes and this part is for filling, permutation. In how many ways nodes can be filled? So this gives you how many different shapes we can get, 5 different shapes. Then n factorial gives one shape can be filled in how many ways? There is n factorial ways. So if the nodes are labeled, then this formula. So that's all, end of the topic. So we have learned number of nodes versus number of different shaped binary trees. So this discussion or this analysis is useful further in other topics. This topic is about formulas. Height versus node formulas. So what is this? If we know the height of a binary tree, what could be the minimum number of nodes and what could be the maximum number of nodes? And vice versa. If nodes are given, what could be minimum height, what could be maximum height? We are going to discuss this one. So first, let us learn if height of a binary tree is given. Then what could be the minimum number of nodes, what could be the maximum number of nodes? So already I have taken a few examples. Let us study these examples. Height of a binary tree is given, height is 1. So height starts from 0, right? So this is 0 and 1. So height is 1. So in height 1, minimum how many nodes are required to reach height 1? 2 nodes. If I remove a node, then only 1 node, it will not be height 1. So minimum 2 nodes are needed to make a tree of height 1. Then in that height 1, maximum how many nodes are possible? 1, 2, 3 nodes are possible. Then likewise, if height is 2, then for making a tree of height 2, minimum how many nodes required? 1, 2, 3. Maximum 7 nodes. Likewise, height is 3, minimum nodes, these many. Maximum nodes, this many. If we don't want a count, we want a formula. So from observation, we can generate the formula. So first, let us check minimum number of nodes. If height is 1, minimum 2 nodes. Height is 2, minimum 3 nodes. Height is 3, minimum 4 nodes. So minimum nodes formula will be height plus 1. See, height plus 1. So minimum nodes n equal to h plus 1. This is one formula we got. Now we want a formula for maximum nodes. 3, 7, 15. We don't find any pattern. Like there was a pattern here, height 2, so 3, height 3, so 4, so height plus 1. But 3, 7, 15, let us observe from this tree. How we got 15? We got 15 because this is one node, and in this level there are 2 nodes, and in this level 1, 2, 3, 4, 4 nodes are there, that is 2 square nodes, and in this level 1, 2, 3, 4, 5, 6, 7, 8, 2 cube nodes are there. So this is 1 plus 2 square plus 2 cube. This answer is 15. So all these nodes when they are added, it is becoming 15. So 1 plus 2 square plus 2 cube is giving 15. So is there any formula for this one? Let me show you the formula. See, this is GP series, A, AR, AR square, AR cube, so on to AR power K. So this is GP series, and all the terms of GP series are added. So sum of the terms of GP series, that is geometric progression. Sum of the terms of GP series means geometric progression series. So there is a known formula for this one. This is A, R to the power of K plus 1. Trees are there with maximum height. So this is 2 cube. So for n equal to 5, how much it will be? You can guess now. 16. Yes, this is 2 power 4. So for any n, how many trees will be there? 2 power n minus 1. So we have learned how many different shaped binary trees can be generated for a given number of nodes. So we don't have to generate the tree, we can use the formula. And one more observation we did, then how many binary trees are possible with maximum height? So that is 2 power n minus 1. Now next, let us generate one more formula for Catalan number. So I will write down few values of a Catalan number. Then from that, let us see how we can come up with one more formula for Catalan number. So first of all, I will take the table of values for Catalan number. See if n is given, then Catalan number Tn, that we know the answer formula 2n Cn by n plus 1. See here, value of n, and this is the Catalan number. So I will take the values of n and write down the Catalan number values also. See if it is 0, then if you put 0 in this formula, you get 1. Then if it is 1, then it is still 1. For 2, it is 2. For 3, we know the answer directly, just now we saw. Then for 4, it is 14. For 5, it is 42. So for 6, I will find out using a different method. I will not use this formula.
We're seeing 10 questions using one concept.